In this video, we shall look at a couple of review problems on Ampere's law. Problem 1. 4 long parallel conductors carry equal currents of 4 ampere, as shown below. The current direction is into the page at points A and B, as indicated by the crosses, and out of the page at C and D, as indicated by those dots. So what this figure is showing is a cross-sectional view of those wires extending all the way from minus infinity to infinity. Very long parallel conductors. Calculate magnitude and direction of the magnetic field at a point Q, right there, located at the center of the square, with sides of length 0.4 meter. First, let's briefly discuss the magnetic field produced by long parallel conductors carrying current. Assume this is one such conductor, so it is very long. It extends all the way to infinity from minus infinity. Let's assume it carries current in an upward direction, I. Assume we want to find the magnetic field that this current creates at that point, say a distance r from the conductor. From Biot-Savart law, we know that the magnetic fields that this current creates will be concentric circles. Like that. There are many such circles. We are just showing a single circle of magnetic field at that distance. The direction of that magnetic field can be worked out from right-hand rule. Let's assume you grab this wire with your right hand. So that is the direction of the current, and the direction of the magnetic field follows the curl of the fingers, like that. So in this example, the direction of the magnetic fields goes like that. Now let's see how to calculate the magnitude of that magnetic field. That's where the Ampere's theorem or law comes in. It says the line integral of the magnetic field about that path equals mu naught, which is the magnetic permeability, times the current enclosed by that path. So, of course, in this case, we take the path to coincide with the magnetic field, like that. Since anywhere on this path, the value of the magnetic field is the same, then we can write this integral as quite simply B dl equals mu naught I. This integral here refers to just the circumference of that circular path. So that integral will simply become b 2 pi r, and that equals mu naught I. And we can solve for the magnitude of the magnetic field at the distance r from where the wire is. Namely, it will be mu naught I over 2 pi r. So this is the expression for magnetic field created by a very long conductor carrying current I at a distance r from the conductor. So when we look at this wire from the bottom, you get a cross-sectional view such as that one. One thing to note is, since this is a circle, the angle between that line and that line, this is the direction of the magnetic field at that point, is 90 degrees. Because this direction is tangential and this direction is radial at that point. Let's come back to the question at hand. Let's figure out first the magnetic field produced by that current at point A, at point Q. Since the current is going into the board, the right-hand rule tells us that at point Q, the direction of the magnetic field would go that way. Due to current B, the magnetic field would go that way. It must be noted and remembered that these two arrows are symmetrical about that vertical line. What about current C? The current C is coming out of the board. So at point Q, it produces magnetic field like that, and it goes exactly in the same direction as that magnetic field. So it reinforces the magnetic field created by current at B. And finally, the current at point D would create a magnetic field in that direction. And at point Q, namely at the middle of the square, it reinforces the magnetic field produced by the current at A. And we note that they are symmetrical with respect to the vertical line, and let's call that angle alpha and alpha. We note that these two magnetic field has an x component going to the left. These two magnetic fields has x component going to the right. Since they are of equal magnitude, the x components would cancel each other perfectly. The y components, or the vertical components of all these four fields, would reinforce each other in that direction. So we can in fact answer the direction of the magnetic field at point Q to be vertically downward. To determine the magnitude, it's sufficient to determine the magnitude of the magnetic field due to one of the currents, take its y component, and then multiply that by 4. So let's do just that. A is at distance r from Q. Now what is distance r? That can be determined from Pythagoras' theorem. This is 0.2 meters, because this is 0.4. Likewise, that is 0.2. So your r is square root 0.2 squared plus 0.2 squared. So the magnitude of the magnetic field due to any of the currents at point Q is quite simply mu naught times the current over 2 pi r. What is the vertical component of that field? This angle here, we know it's 45 degrees. How so? Because this length and that length are the same. Arctangent of one is 45 degrees. Since we know the direction or the angle between the radial line and the tangential line is 90 degrees, then this angle must also be 45 degrees. That means alpha has got to be 45 degrees. So the vertical component of that magnetic field, let's call it Vy, is mu naught I over 2 pi r cosine 45, which is 1 over square root 2. That means the total magnetic field at point Q is 4 times of that. So 4 times mu naught I over 2 pi r square root 2. Again, this number 4 is due to the contribution from A, B, C, D, which all produces the same component of magnetic field at point Q. So now let's put in the numbers. The total magnetic field at point Q is in this direction, namely downward. The magnitude is given by 4 times mu naught. Mu naught is 4 pi times 10 to the power minus 7. The current for each is 4 ampere. Divide by 2 pi square root 2, and r is given by that, which is square root 0.2 squared plus 0.2 squared. And the answer is 8 times 10 to the power minus 6 Tesla, or simply 8 micro Tesla. That solves the problem. Problem 2. Figure below shows a cross-sectional view of a coaxial cable. The center conductor is surrounded by a rubber layer, which is surrounded by an outer conductor, which in turn surrounded by another rubber layer. So the rubber layers are somewhere there and outside. The current in the inner conductor is 2 ampere into the page. That's that one. And the current in the outer conductor is 4 ampere out of the page, as indicated by these dots. Determine the magnitude and direction of the magnetic field at points A and B. So let's look at point A. These are long cables. So the magnetic field at point A is created, according to Ampere's law, by only the inner current, namely the 2 ampere current. And of course, this magnetic field, shown in green here, appear in concentric circles. Using the right-hand rule, at point A, the direction of the magnetic field will go downward, like that. So let's apply Ampere's law to this path in green. So it's going to be the magnetic field at that distance, multiply the circumference of that path in green, and that path has a radius of 2 millimeters. So let's just write as 2 pi r equals mu naught times the current enclosed by that green path. In this case, it's just 2 ampere. 4 ampere appears outside that path, so that doesn't contribute. Only 2 ampere contributes. And you can solve for the magnetic field at point A. It's mu naught, which is 4 pi times 10 to the power minus 7 times 2 over 2 pi r. R is 2 millimeters. That is the radius of that path. Convert that into meter, you get 2 times 10 to the power minus 3 meter. And the answer is in Tesla. When you do the sum, you get the following. 2 times 10 to the power minus 4 Tesla, or quite simply 200 microtesla. So we record the answer over here, magnitude 200 microtesla in the direction downward. Now let's look at point B. What is the field there? We can use the path, a circular path, through that point B like that, whose radius is 6 millimeters. The magnetic field at point B has 2 contributions. One is due to the central current, the other one is due to this 4 ampere current. Now let's apply Ampere's law. This is the path. The circumference of that path is 2 pi. The radius of the path is measured from here to there. It's given by 6 millimeters. So 2 pi 6 times 10 to the power minus 3 meter. And that equals to mu naught times the net current enclosed by that green path. So in this case, the net current would be 4 ampere minus 2 ampere, because the directions of this 4 ampere current and 2 ampere current are opposite. So the net current enclosed by that green path is 2 ampere. So as if the net current is coming out of the board. And if you have a net current that is coming out of the board or the plane, then using the right-hand rule, the direction of the magnetic field at point P is going up. And we can even solve for that magnitude, which is 2 times mu naught. Mu naught is 4 pi times 10 to the power minus 7 over 2 pi 6 times 10 to the power minus 3. 2 pi times 6 times 10 to the power minus 3, which will result in 6.67 times 10 to the power minus 5 Tesla, or quite simply 66.7 microtesla. So the answer for part B, the magnetic field at point B, is 66.7 microtesla in an upward direction. And that solves the problem. Thank you for watching.